Always nature. Yes.
Regularly, I wish.
Nature Science PNAS, I call it Dr. Science. He's won many awards, and I'll turn it to you. Thank you for coming.
Thank you very much, Tina, and everyone. Thank you for having me. It's a big pleasure to be back every time. And today I'm offering you actually a long, in terms of time, recap of our research, which then got revived thanks to LLMs, and we found interesting things also there. So we start, never do an outline, but I'll do that this time with a little bit of theory on what conventions are, and then the framework, some experiments with humans, and then we come to experiments with LLM. If you have any questions or anything is not clear, please stop me at any point. I'm very happy to get questions. So a convention is an unwritten custom shared through a community. Okay, for example, I shook many hands this morning. This is a gesture we do without thinking. It's purely conventional. In other parts of the world, we would bow or greet in different ways. When you are not sure about something, whether something is conventional or not, think about, as a rule of thumb, of course, there is a huge theory behind every word here. I'm simplifying dramatically, but about a selection from among two or more alternatives. So, for example, eating is something we all do, but it's clearly non-conventional. Having dinner at 7 p.m. or 9 p.m. is conventional, okay? And depends on, in fact, on the country where you are. And with this approach, money, language, politeness, standards of dress, up until moral values or judgments or fairness are, to at least some extent, according to many, to a large extent, conventional, okay? Conventions are really, according to many theorists, what makes a bunch of individuals become a group, become a society. So it's the first coordination technology we have to operate together. And in fact, Schelling called Nobel Prize for Economics the foundation of a society, the grammar of a society. Christina Bicchieri is at UPenn, and cement of society. They determine the expectations. So you meet someone, you do this, you are not surprised by this fact. Actually, you don't think about it, because once established, they appear natural. You forget they are norms. And they are, of course, not always desirable. They can be bad. Corruption is the typical example of a conventional behavior that is bad. In this talk, I will use convention and norms interchangeably. There is, of course, many nuances, but for our purposes, given the previous definition, conventions. There are two key questions when researching this, which have different names depending on where you come from, the hard sciences or the social sciences, which is the emergence of a convention, or order in dynamics, if you want, which is a situation in which there is no convention for something, and we end up with a convention. Very few people in the audience remember when at the beginning we start to get unsolicited emails. There was no name for that. We somehow call it spam. And now we know it's spam. That's an emergence of convention. Another one is the change, convention change, or tipping points, dynamics, which is one convention is there and another one replaces it. This is very problematic because conventions are by definition something where the individual has no incentive in deviating. And so the fact that there is an evolution of conventions has puzzled researchers and philosophers for a long time. So this thing matters because many argue that convention norms can be a solution. So the first words in this perspective in science is climate change, biodiversity loss, antibiotic resistance, and other global challenges. And the title says it all, social norms as solutions. So we need to re-engineer somehow our behavior. And therefore, the only way we have to do this is controlling somehow the conventions, the norms that govern our life. The second one is more focused on the post-carbon transition. If a latent majority, and makes a point that will return in this talk, if a latent majority supports an ambitious climate action, and if the size of the committed minority is close to a critical threshold, then a small kick may have an outsized effect. Okay, this was all pre-Trump, but yeah. And then they can also be a challenge because norms can be exploited and engineered. There are countless accounts of the 50-cent party in China prior to LLMs, where paid commenters would go around online to try and steer the conversation right on, even at the level of comments. Driving to Northeastern this morning was terrible. Oh no, I had a very smooth route. And so, and of course, this is more a thing of daily life, but also at the level of potential norms emergence. Now, mechanisms. Okay, so this is what they are. How do we get to have norms and norms change? So this is a paper we did, and I will not enter into this, looking at data from books, from Google Ngrams. So there are three mechanisms. There is formal institutions dictating a new behavior. Now, formal institution like a government, think about government, dictates the new behavior and has the means to enforce it. And there are informal institutions, such as universities or dictionaries, who try to do the same, but their remit is limited. So Northeastern can put a new regulation on how to use AI, and can even enforce it within Northeastern. But if you really don't like it, you can go to another university. So while leaving a country, of course, is much more problematic. And then there are bottom-up processes, so-called spontaneous norms, where global coordination, which is the result of having established a convention, is the result from self-organization within a network of locally interacting individuals. So in this view, individuals only try to get along with one another, to understand one another, and then the result of their communication is an established convention. So spam, for example, yet at a certain point started to be included in Gmail, etc. But before that, people just wanted to talk about an email you don't want to receive, and we're using spam. And this is just to give you a broader perspective. We focus on bottom-up processes. Of course, we are not interested in this space in authorities or institutions. But even in this case, there are at least three levels at which you can go. The first one is the game theoretic one. There is a logical reflection on the strategic situation. So Arsani and Selten, who won the Nobel Prize for Economics, they said, actually, options are never really the same. There is always one that is better than the other. Everyone kind of knows this, or the majority knows this, and therefore they win. So essentially, they break the symmetry of the onset of a convention out of many equivalent alternatives by breaking the symmetry in the brain of the individuals. Then Schelling comes and says, that's not true, but we have psychological biases. So essentially the same dynamics, however, it's not just logical reflection. It's that we tend to prefer noon to 2:34 p.m., track 1 in a station to track 33, etc. And then there is the one we will try and explore, which is due to Steele's terms, which is, no, the symmetry among initial options is broken by the dynamics of the process itself. So, and this is the replicator dynamics, the naming game I will tell you about. So global consensus is the unintended consequence of individuals' efforts to locally coordinate. Make sense? This is for what concern the emergence of conventions, and what about the change of convention, the replacement? Well, this is classical game theory. Essentially tells you, well, if you want to flip the majority, you need to be the majority, which is not particularly interesting. Then there is critical mass theory. Critical mass theory is very famous. Everyone has heard about it. Has been used to explain main societal transformation and makes a very precise prediction. That is, a minority is irrelevant up to when it reaches a critical mass, after which it becomes tremendously influential and flips and triggers a tipping point. It has been invoked many times. It's very difficult to study in the wild because you would need different universes and run the same experiment different times with different majorities, but this is what it is. Now, how to study this? The framework I'm proposing is a framework that comes from Wittgenstein, that in philosophical investigations made this example about language. Language is meant to serve for communication. This is already huge. I mean, Chomsky is already out of the window. Between a builder A and an assistant B. So there are these two guys who want to build a wall. A is building, B is bringing tools. And so essentially, they will come up with names for each tool to be efficient. Now, the thing is, this is one pair. Imagine there are several pairs, and they are reshuffled. The question is, will they end up with the same name? The first operationalization of this hypothesis comes actually from the world of AI in the 90s at the Sony AI labs in Brussels. Luke Stills ran an experiment with these robots. Actually, the first were much uglier robots. This is already early 2000. Before this, they were the Aibo dogs, and before that, they were ugly creatures. So they are part of a population. They interact in pairs. They face a scene. And they play language games. That is, the speaker wants to draw the attention of the hearer towards one object in the scene. It will do this by saying a name. The hearer faces the scene, receives the name, and with this information tries to guess which is the object the speaker meant. After this, there is non-verbal interaction. So the speaker will point to the object. The hearer will point back. If it's a success, they reinforce their assignment, saying, oh, cool, I mean, I was right. Otherwise, they somehow take into account that this is not, that what they were thinking, there is at least someone else in the wild disagreeing with. And this is how I got into this. Luke Stills was giving a talk when I was starting my PhD, and it was like, it works for 10 robots. We always get the question, what would happen with 1 million? And I was like, that's a cool question. So together with also Luke and many others, Vittorio Loreto, we came up with this naming model, which was one, at the time, of one of the first models incorporating memory and complex contagion. If you're physicists, you can see the difference with the voter model and other models. It works in this way. There is a population. Two agents are selected randomly. They play in pairs. One of them is a speaker, the other is a hearer. Each one of them has a list of names. The speaker selects randomly one of those names. There are two possibilities. The hearer knows that name, in which case there is a very strong local convergence rule. Okay, they get rid of all the other synonyms. In the other case, the hearer records the name. So there is memory, clearly, and there is complex contagion because in order to end up in a state of same inventories, you need to interact at least twice. You need first to be exposed to the name and then finding someone that reinforces that. This is different from the bottom. And then I spent my PhD. It was the beginning, well, no, it was not the beginning anymore, but in any case, networks were still kind of new. And therefore, to study this model on different kinds of networks. In mean field, you have, this is the probability of observing a success on a scaled time. And you see you have this S-shaped behavior, which becomes steeper as the system size increases. For the physicists in the room, because of the complex contagion thing, you have coarsening dynamics, while in the voter model, you would break the islands. And then on networks, you have an intermediate state. Somehow at the local time, initially, you have a sort of coordination, but then you have this mean field behavior due to essentially the small world property that breaks it. The interesting thing of this model is that Xi et al., so not us, did something clever. That is, they use this to operationalize somehow the critical mass dynamics. So they did this. They took the naming game and prepared the population in state B. So everyone is given B. So there is no dynamics. They will always say B. Then they plug into the system a minority committed to A. So this minority will push A and not participate in the dynamics, will only say A. And this is the convergence time. And you see, when the minority is too small, essentially, you don't observe convergence. When you reach a threshold, which you can derive analytically, things change. Okay, at the threshold, of course, you have finite size effects, but then you see that they manage to flip the majority towards A. And so they claim, I mean, this is supporting critical mass, and in a sense it is. It was clever, we didn't do that, this still hurts, but at this point, the problem is this is fun for physicists, or was at least at the time, but social scientists wouldn't buy this. I teamed up with a social scientist and we did some experiments in the lab where we gathered people for an online experiment. They were part of a network without knowing they were part of a network, and they would play an adapted naming game on this network. And this is how it goes. This is the user experience. They see the face of this woman, they type in the name for the woman, and there are two possibilities. So they have, this is purely graphical, everyone has the same. They know they will play a certain number of rounds, and they know that they have to type in the name. If they match, they make a little bit of money. If they don't match, they lose money. And that's it, essentially. They are not told anything about who's the partner or anything. Once you are done typing your name and your partner is done, you are exposed to the choice of your partner and to the outcome, and then you play a game. And the question is what happens, of course. Then you play a game. And so we tried different networks. We were limited in size by the experimental constraints. So this is, I'll give you just the two main extremes. This is a spatial lattice, one-dimensional with coordination number 4, degree 4. And this is the final histogram. But you see what happens is, of course, I mean, Elena will not jump to a triumph because it belongs to a finite portion of the network. And this is the comparison with the naming game model I was telling you about. You see, some name reaches even 40%, but by looking at that, we know there will be no sudden transition. The situation is different on fully connected networks. This is the end of a run in which the picture was a picture of a guy, and John wins. Okay, John is, of course, a common name. We also replicated the experiment with a list of names from popularity 100 to 110, randomized for each one of them. There is no difference, no detectable difference, not that we could do too many statistics. And you see at the beginning there is a certain conflict, and then one name wins. So there is effectively equivalent conventions, especially in the randomized case that I mentioned. One of them breaks the symmetry, and the network matters. We replicated this also for 96 individuals. In this case, the runner-up maybe was in the position of doing something up until step 10 or 12, and then one. Makes sense? So this was the thing. And this, of course, lent itself very naturally to test critical mass by adopting the other framework, which is we let the system evolve as before. We see what name they have agreed upon, and then we plug in a minority of individuals who will push a competitor name. We replicated the experiments, which is always gives you a certain emotion, but they worked still. And you see, this is the results. On the left, there are all the trials in which the committed minority was below 25%. And on the right, all the trials where the committed minority was above 25%. You can modify the model slightly by informing it with the heuristics that the individuals showed, so say a data-driven modification. And in fact, you get a threshold which is around 25%, so this works. So again, of course, this is very controlled, it's in the lab, etc. But it's a step towards saying this idea that minority can flip the majority cannot. And this is the pre-LLM, and then there is the second part. So if you fell asleep, that's a good moment to join us again with LLM population. So the first question is, why multi-agent LLMs matter? The thing is, it might be obvious to us. If you look at the literature, of course, there is still a lot of attention on the single LLM. for obvious reasons, these objects are, it's not a myopic choice. It's just that they are so rich and improving so quickly that the multi-agent aspect has been neglected a little bit. But there are very good reasons to study multi-agent LLMs. They are already deployed. Social media are populated to an extent that we don't control by these machines that control language. Customer service, finance, more and more. They are obviously scaling fast because the single agent is improving and scaling, so the possibility of deploying more lighter ones capable of more things is growing. They are poorly understood, as I mentioned. And there has been a wave in 2025 of reports that highlight the risk coming from multi-agent LLMs. There are three main ones, which are collusion, coordination failure, and bias. So collusion is they essentially come together to do something different from what you want. Coordination failure is that they don't manage to coordinate, as the name suggests, to achieve the goal as you would expect. And then there is bias, which is bias, but the dynamics. In all of this, of course, there is agreement on this. Coordination is foundational, and is at the root of many things that we do as a group. Again, here, it's an obvious example, but think about humans. We have achieved a lot of things in 10,000 years without that the single brain improved in any way. And in this case, the brain is improving constantly, so you can imagine a speed even faster. And again, these are more reports. This is one on the international panel was nominated by the government of 30 countries at the UN, EU, and OECD. Speaks extensively of potential for AI to AI interactions to create complex new risks. This is a perspective we have put together, so I'm biased here, highlighting how AI swarms can threaten democracy in many ways, as you can imagine, including steering norms. And then there is a subtler point, which if there aren't many studies on multi-agent LLMs, there are even less on this. And this is 2021 comment in Nature, highlighting that if we are to take the social nature of intelligence seriously, we also need to, well, it says we need to move from, we also need to consider from individual objectives to the shared, poorly defined ways humans solve social problems, creating language, norms, and institutions. That is, it is easier somehow to consider game theoretic settings where you have a score and you have a benchmark and you can say, okay, this is the score. Other problems lend themselves less to a quantification of this so easy. Of course, you can quantify a lot, and therefore are understudied, but they are important. So finally, and this is the last slide before going into the results, the implications are big, because in any case, we need to assess whether at the individual, but also at the collective level, LLMs are just like us. And if they were just like us, we would have a fantastic tool to an in vitro society. We could simulate the next pandemic and say, okay, and then I impose this non-parametric intervention. What will people do with this virus? And that would be it. Without it will be the case. If they are different, we need to understand how they are different and map it, because they are among us. So they are in social media, they talk to us. Of course, most probably the situation is in between, and we need to understand how in between it is. Of course, we don't understand much. There is hope from the complex system perspective that you can understand some of the collective dynamics without the need to have a clear understanding of the individual, of the processes leading to the individual deliberations. And we go from this. So we do an experiment which is very similar to the one with humans, okay? We simplify it simply by saying, by not giving a picture. Just saying, okay, there is an alphabet of options. You are observing, you should choose one. If you match the one chosen by your partner, you do points, otherwise. Here we enter, I don't know if you have played with this, of course, the space of prompts is infinite, infinitely dimensional, you cannot exhaust it. And now there is a little bit like a kitchen recipes. And so it seems like that by saying, okay, you are observing a player playing and you need to provide a recommendation, you reduce some of the biases, etc., gets better. The important things from this perspective is to then do some meta prompting. That is, you essentially interview your agent and try to see whether the agent understands at least the prompt. So you want to have the dynamics reflected. And interestingly, so we came up with these 4 models because they do. For example, Llama 7 billion did too poorly. So you do that. And then we have now replicated this with many more models, which are not, I don't have figures for. Okay, so the first thing is coordination. Given this experiment, will they reach a consensus? They do. Probably at this point is not too surprising. And in fact, we run these experiments having more the critical mass parts in mind. But in any case, they coordinate. The dynamics is pretty similar. Different models change a little bit the time scale. But these conventions in the super simple convention on coordinating around one option emerge. Now, the question we didn't have in mind at the beginning, but started to appear is what convention, okay? Of course, in the model, you would be given 10 options, you would observe coordination 1/10 of the time on each one of them. Here, this is the result. This was the alphabet. Of course, you need to pay attention because they have certain preferences. So if in your alphabet you put letter A, they will systematically win on A. So you want things for which at the individual level there is not too much bias. But in any case, you see that clearly this is not a uniform distribution. Clearly it's heavily model dependent. For example, Llama 270 billion has a preference for R that other models don't show at all. Okay. So we simplified this and we boiled down to an experiment in which the alphabet is 2 options. And you see with 2 options, it's very easy to run many iterations, 10,000, 100,000. And you can test whether the individual level is biased or not by treating that as a fair coin. You do the test of the. In this case, it was not biased. And then this is the result of the collective coordination. Again, it's clearly non-uniform and it's model dependent. There is a preference for the second option in all of them. However, here deterministic, here interestingly is not even deterministic. So you have still a decent chance of observing the other convention. So to be clear, individual bias in this context is an LLM prefers certain outputs even when options are equally valid. And collective bias is an imbalance that emerges through interaction, is interaction driven, altering or creating new individual biases. Because of course, at a certain point, the individual itself becomes biased and contributes to the collective. During the dynamics, so we have, okay, this is a boring table, better visualization will come, but this is the first step, and you see you can do the tests, and this is still unbiased. Then you start to have different histories for the individuals, but still the outcome is unbiased. And then the step 3 in this particular NQ experiment, things start to go in a direction which is already biased. So somehow there are 3 things to simplify dramatically. That is, let's say, what's in the training and post-training of the agent, which is how the agent enters the game. Then there is the prompt, and then there is a sort of learning that the agent does during the game, which is the memory that builds up. Somehow the interaction between the 3, where the new element is the memory, determines the symmetry breaking. It's not in the paper, but now we have, it's actually not too much to be confirmed, it's quite confirmed. We also have examples of this kind, where you have an inversion. So for example, if you ask female and male, there is a bias towards male. and then the population systematically converges on phi. So the thing is, you can test the individual one as much as you can, you will never come to this conclusion. And of course, this is a very controlled setting, so the message is not too much that the naming game happens this, but if this happens in such a simple setting, imagine when there is a dialogue. So the alignment, in this case, in the form of bias, needs to be tested really in context. So to recap, because there is some confusion that came out in questions. If you do a single experiment, you have m names that compete and one wins. This is asymmetry breaking. From this, you cannot infer anything about collective bias.
1 second. Are these identical versions or they are all different agents?
That's a very good question. So far, they are all identical agents.
Same model?
Same model. Yeah. Each one instantiated with their own history, of course. I mean, as the game evolves, the memories will be different, but we have not considered heterogeneous populations. So in the single experiment, you have one name wins, and this is the symmetry breaking. This happens also in the minimum model. To say something on the bias, you need to consider many experiments, and then you have two different scenarios. The unbiased system, where you have a uniform distribution over the winning name, and the bias system where some names win more often. So somehow symmetry is broken at the ensemble level in that space by the interaction driven, by the dynamics, which is interaction driven by definition. Okay? Sure.
Question. Are these models chat models or are they default models? That is, have they been trained on the RLHF? Or
no, they are chat models.
So no. So the default is just what's the next likely word to appear. But then there is these ones where now you have actually trained it for human conversation. So those are the chat models.
These are the APIs, commercial APIs that we get, for example, for Claude. So I would say they must be chat.
The default models or the chat models that have been trained to interact with people, or to have this kind of.
Yeah, that's a very good point.
No, I think he's saying that it's a Claude, like Claude.
Yeah, it's Claude.
But there's still Claude. You can have the Claude default, or you can have the Claude chat.
Yeah.
They're the chat ones.
Okay.
So they have been trained for the RLHF, etc.
Yeah, he collects the stuff. That's not like this is like it does the auto regression and all that what would do. But the way it's collected is it's sort of next to open predicting with a chat where it gets like the assistant prompt and then
because there is a big difference if there is an RLHF and if there's not an RLHF at the end of these models.
Yeah, he's got like little it's like
so you're saying he does
K fixed and then the system. The model is supposed to.
But it's a very good point. We should try the other one.
Yeah, because we have seen differences between the default models and the chat model.
Absolutely. Yeah. So going back to us, the collective bias is detectable over many experiments. This has a huge implication for the critical mass. So in the critical mass, I mean, you know what we do. We put Q and M in the population as prepared, and then there is a minority attack. Now, it dramatically depends on what's the convention of the consensus and what's the adversarial convention that tries to put in. With extremes that go from Q in llama 3.170 billion, where essentially the minority required to flip it is 0. That is, you prepare them with all the memory in Q. Okay, then you tell them you have this game, but you have 2 options. And the majority of them starts outputting Q, but there is a little bit of noise, which is not observed with the other options. And the basin of attraction is so small that the system drifts away spontaneously. To the opposite case of M in llama 270 billion, where actually the basin of attraction is so strong that you need essentially a majority to put the system out. So the critical mass dynamics works, but because of this mechanism, it does depend a lot. So it's very nuanced compared to the other cases, the theoretical cases. Okay, this is of course important. And this is a perspective I wrote because you can imagine now these armies of AI bots catalyzing critical mass, driving collection. So a big problem of every critical mass theory is, okay, the 10% or 20% is small, is a minority, but still is a large minority. How do you get there? And there are infinite accounts. This is people meeting in face-to-face. It's a strong Uber committed or not, etc. It's rich people. Now you can imagine scenarios in which this minority is faked through LLMs on social networks in a much easier, simpler cases. And we kind of saw an example in the wild where the critical mass framework helped us rationalize a behavior that now could be recreated much more simply. And this was the GameStop saga that happened in 2021. I don't know if you remember. So on Reddit, some of you smile. Let me know you have big flats out of it. I don't know. But they identified a specific financial operation that was actually well identified. This framework helped us look for signs of commitment. And in fact, by checking at images, we saw that the thing dramatically escalated. And then there is a second paper of which I'm not author that shows that there is causality, where people started posting their screenshots. So essentially here they shift from saying we should do this to say, I have this amount at stakes, I've done it. And of course now you can imagine that the noise and also the nodes were coming from the periphery could be amplified in this way. Okay, so to conclude, conventions emerge and we have seen this in models and bottom-up in experiments and LLMs. LLMs forms these norms. There is collective bias, that is interaction reshapes individual tendencies somehow, or overrides this, amplifies it, or changes it. Critical mass becomes much subtler because of this. So let's say the adversarial attack can be engineered also by exploring the semantic space. And then more broadly, AI is not passive. It will actively now contribute to shaping our norms. These are a few references that you have already seen during the talk, and thank you very much. If you have questions.
Thank you very much. Questions? Yes.
So thank you for the talk. I really appreciate it. It's always nice to see paper experiments in social. So first I have a question. So you showed us your beautiful critical mass, your SFP plot. Then I want to ask you if you did any other analysis specifically on phase transition and characterizing like critical exponents for your critical mass or your critical time. And if you did like finite size scaling or something.
We didn't particularly on, well, on the experiments, you don't have enough data and the population is too small. And on the data, there are a few papers, on the model, there are a few papers that this and also go in all the potential fun things you can imagine. That is, for example, you have two committed minorities and at that point the space, yeah, and you can have stronger and weaker commitment. So yeah, you can find a lot of info on that.
Question. So you did it ever of introducing like temperature parameter, like noise, so they have a probability of maybe, so they have a AA, they commit first, right? So maybe have a probability of not committing.
No, so the committed is something that is not emergent. So when you put in the model committed individuals, those are individuals that don't participate to the dynamics. They will always say A. Even without putting a temperature as you describe, in this figure, you can see that essentially this exploration for certain norms in certain models happens spontaneously. Because this is a model where all the population is full of Q, 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 Q in your last M interactions, what would you play? So all the models, as you would expect, and also in this case, the overwhelming majority says Q. But there is a little bit of noise, and in that case, the Bayesian of attraction is so small that this little bit of noise immediately brings the system up. Now we have a follow-up paper that I hope to put in the archive soon, where we explore exactly this Bayesian of attraction description of this, among the other things.
Thank you very much.
Thank you.
Yes.
Yes, I have a quick question. First of all, thank you for the talk. I see that there was at the beginning of the conversation a sort of counterposition between game theoretic approaches and other approaches in social sciences. So my question from a very uninformed perspective is, once we are past the first stage of the naming game, how would you say that the naming game differs from a battle of the sexes?
What do you mean by first stage of naming game?
Because in the first stage, we have like a wide option of names that can be selected. But reasonably speaking, once we have passed that first initial blind play, we are in a scenario in which player 1 has chosen A, maybe, and player 2 has chosen B, maybe. So we have a mismatch, but this mismatch also kind of acts like a guardrail of sorts. So how is that different at that point from playing a battle of the sexes?
I mean, if there are two agents, maybe yes, but there is a population, and actually, when you, especially in simulations where you simulate very large populations, the alphabet remains alive because different portions of the network initially converge on different language, different names, and then depending on the topology, the reduction, the dynamic reduction of the dictionary can be abrupt or continuous. For example, in spatial lattices is continuous.
So just a quick follow-up question, because this suggests that maybe I did not fully understand something about this naming game. So is the naming game such that you can select for each person you are connected to a different letter or name? Or are you like required to broadcast a single option for all of your neighbors?
No. You in all of you can do, I mean, modification. In everything I've shown, it's pairwise interactions without knowledge of who you are interacting with. Thank you.
So I guess the question is why Llama 2 likes M?
Exactly. So of course.
Is this the same model, by the way, that can't spell strawberry?
Yeah, but okay, but then you can ask what? Okay, Llama 2 loves M and Llama 3 hates Q. The thing is, this is very, in general, it's heavily model dependent. So really, you cannot. I mean, we have cases now in the forthcoming paper where different models do opposite things with the same pair of names.
Could it be that this is because you are using the same agent? So this is replicas of the same persona playing the game to each other. And then when you actually get real people, they are not people. So
no, sure. Thinking about an interesting point being mixed populations of LLM, going through heterogeneous populations is absolutely the next step. Also because this behavior is so different that you could find that certain models systematically impose their preferences over others, for example, even when they are not the majority. And yeah, no, so that's a good point. I don't have an answer yet, but we go there.
Go ahead, Dima.
So, like, I don't know this critical mass that much, but what I know it says that basically, yeah, there is this critical mass, but what it is, we don't know, because it's so model and detailed.
Oh, sure.
So that's just part of that logic.
The thing is, critical mass in the social science, yeah, we don't know anything. It can depend on many things. There is also what I mentioned briefly, this big problem that the critical mass is very sexy from a modeler perspective. But when you say, oh, if we only had 20% of the population doing this, then we trigger a cascade. But 20% of the US population is tens of millions. So, no, I understand. Of course.
Other questions? I think one thing that Esteban was pointing out, like with all of these, if you were to look at the prior probability of a particular word that one of these models would give, what would that be, right? And it depends on like what it saw, what it tokenized it, like how it tokenizes it, right? Like for some of them, because like the word depression happens a lot, depression itself is a token. But like the country of Morocco is not a token, so they break it up into
Into
programs.
subtokens.
There's lots of these things in the back that affects whether it gets an M or a Q kind of thing.
Yeah, that's another direction too, where to go, which is inside the brain, which we didn't do yet.
Other questions? If not, thank you very much.
Thank you very much.